new payload as an echo reply. Destination host becomes a source host. A packet is created including the source host, the destination IP address, protocol field, and payload. The destination device is now host A. IP checks to see whether the destination IP address is a device on the local LAN or on a remote network. Because the destination device is on a remote network, the packet needs to be sent to the default gateway. The default gateway IP address is found in the registry of the Windows device, and the ARP cache is checked to see whether the hardware address has already been resolved for an IP address. After the hardware address of the default gateway is found, the packet and destination hardware addresses are handed down to the data link layer for framing. The data link layer frames the packet of information includes the following in the header: the destination and source hardware addresses, the ether type field with 0x0800 IP in it, the FCS field with the CRC result in tow. The frame is now handed down to the payload. Sorry, the frame is now handed down to the physical layer to be sent over the network medium one bit at a time. Time for the router to route another packet. The router's Ethernet 1 interface receives the bits and builds a frame. The CRC is run and the FCS field is checked to make sure the answers match. When the CRC is found to be okay, the hardware destination address is checked. Because the router's interface is a match, the packet is pulled from a frame and the ether type field is checked to see which protocol at the network layer the packet should be delivered to. Protocol is determined to be IP, so it gets the packet. IP runs a CRC check on the IP header first and then checks the destination IP address. In this case, the router does not know how to get to network 172.16.10.0. The exit interface is Ethernet 0, so the packet is switched to interface Ethernet 0. The router checks the ARP cache to determine whether the hardware address for 172.16.10.2 has already been resolved. Because the hardware address to 172.16.10.2 is already cached from the originating trip to host B, the hardware address and packet are handed to the data link layer. The data link layer builds a frame with the destination and source hardware address and then puts IP in the ether type field. A CRC is run on the frame and the result is placed in the FCS field. The frame is then handed to the physical layer to be sent out onto the local network one bit at a time. The original source host, now the destination host, receives the reply packet. The destination host receives the frame, runs a CRC, checks the hardware destination address, and looks in the ether type field to find out whom to hand the packet to. IP is the designated receiver, and after the packet is handed to the IP at the network layer, IP checks the protocol field for further direction. IP finds instructions to give the payload to ICMP, and ICMP determines the packet to be an ICMP echo reply. ICMP acknowledges that it has received the reply by sending the exclamation point to the user interface. ICMP then attempts to send 4 more echo requests to the destination host. Testing your IP routing understanding. I want to make sure you understand IP routing because it's really important. So I'm going to use this section to test your understanding of the IP routing process by having you look complete at a couple of figures and answer some very basic IP routing questions. Figure 9.4 shows a LAN connected to router A, which in turn is connected via WAN link to router B. Router B has a LAN connected with an HTTP server attached. The critical information you need to glean from this figure is exactly how IP routing will occur in this example. The destination address of a frame from host A will be the MAC address of FA0/0 interface of router A router. The destination address of a package will be the IP address of the network interface card NIC of a HTTP server. The destination port number in the segment header will have a value of 80. That example was a pretty simple one, and it was also very to the point. One thing to remember is that if multiple hosts are communicating to the server using HTTP, they must all use a different source port number. This is how the server keeps the data separated at the transport layer. Figure 9.5 shows a network with only one router but two switches. What you want to understand about the IP routing process here is what happens when host A sends data to the HTTPS server. The destination address of a frame from host A will be the MAC address of the FA0/0 interface of the router A router. The destination address of a packet will be the IP address of the NIC of the HTTPS server. The destination port number in the segment header will give a value of 443. Notice that neither switch was used as either a default gateway or another destination. That's because switches have nothing to do with routing. It's very important to remember that the destination MAC address will always be the router's interface if your packets are destined for outside a LAN, as they were in the last two examples. Static and dynamic routing. How does a router send packets to remote networks when the only way it can send them is by looking at the routing table to find out how to get to the remote networks? And what happens when a router receives a packet for a network that isn't listed in the routing table? It doesn't send a broadcast looking for the remote network. The router just discards the packet. There are several ways to configure the routing tables to include all the networks so that the packets will be forwarded. Understand that what's best for one network isn't necessarily what's best for another. Knowing about and being able to recognize the different types of routing will really help you come up with the best solution for your specific environment and business requirements. Look at figure 9.6, you can see that we can configure a router with either a static or dynamic routing. If we choose static routing, then we have to go to each router and type in each network and the path that IP will use to send packets. However, the static routing does not scale well in large networks, but dynamic routing does because network routes are automatically added to the routing table via the routing protocol. Dynamic routing protocols break up into many different categories or types of protocols as shown in figure 9.7. The first split in the dynamic protocol branch is the division of interior gateway protocols and extended gateway protocols. We are going to talk about each protocol and category, but for now the difference between IGP and EGP is interior or exterior routing of an autonomous system AS. An autonomous system is a collection of networks or subnets that are in the same administrative domain. This is another way of saying an administrative domain is within your company's network, and you control or administer all the subnets that are within it. You control and set the policy for what happens in the network or autonomous system. I hope you can now see that an IGP operates and routes within an AS, and an EGP works outside or between more than one AS. The most popular protocol for an EGP is Border Gateway Protocol, which is typically used by ISPs or really large corporations. As an administrator of a small or medium network, you'll probably never use BGP. The thing that comes to mind first is the amount of time and energy we save configuring routers. We won't have the energy to go to every single router and define for it what with a stashing route, what and where by every destination network is, and that were the only way to configure routing. There would probably be a lot fewer of us interested in doing this for a living. Thankfully, we have routing protocols that do much of the work for us. We still have to know what the routing protocols are going to do and how they will do it, but the protocols will take care of most of the updating and sending information to each other. That is the end of the EGP branch of the tree, but the IGP branch continues to split out as we go down further. Looking at the figure 9.8 with the IGP split, you can see that there are two primary categories: distance vector and linked state LS routing protocols. In the distance vector category, for example, we have RIP and Interior Gateway Routing Protocol IGRP. Under the link state category and the non-proprietary OSPF and intermediate system to intermediate system that were designed to work in larger internetworks. Now in figure 9.9, you can see from the diagram that there is a third category, the hybrid protocol category. The only protocol under this category is EIGRP. It is a Cisco proprietary and uses the features of both DV and LS. The Network Plus objectives list BGP as a hybrid routing protocol as well because it can work on internal networks as well as external, but it's really an EGP. Just keep this in mind. Summary. In this chapter, Summary. This chapter covered the IP routing process in detail. It's extremely important that you really understand the basics we've covered in this chapter because everything that's done on a router typically will have some type of IP routing configured and running. You learned in this chapter how IP routing uses frames to transport packets between routers and to the destination host. Understanding the process of how packets and frames traverse a network is critical to your fundamental understanding of IP routing. I covered the basics of IP routing. I went through some examples to test your understanding and to emphasize the importance of the IP routing fundamentals that you need. I finished the chapter with an introduction to the static and dynamic routing and explained IGP and EGP as well as the difference between distance vector and link state routing protocols. So I'm going to leave it here today for this video. If you liked listening, please consider like, sharing and subscribing, and thank you very much.